We were talking about frequency response methods for analysis and design of control systems, and we learned that there are different tools which can be utilized for analysis and design of control systems. Among these tools, Bode diagrams, polar plots, and Nyquist diagrams, these are important tools. We have already talked about Bode diagrams in our previous two lectures, and in today's lecture and hopefully in the next lecture we shall talk about polar plots. So you remember that Bode diagrams, these are the plot of frequency response of a system, and in Bode diagrams you had two different graphs, one for the magnitude frequency response and the second graph was for phase frequency response. In polar plots, you represent both the information, that is magnitude frequency response and the phase frequency response, in a single graph. So you remember that the frequency response of a system is given by this relation, where this magnitude, that is called the magnitude frequency response, and this part is the phase frequency response. In Bode diagrams, you had two different graphs, one for the magnitude frequency response and the second for phase frequency response. However, in polar plots you have a single graph to give the information about both of these responses, that is frequency response is plotted in a single graph. So you already know that this g of j omega will be a complex number, and complex number can be represented in a complex plane. So here we have a complex plane with real axis and the imaginary axis, and this complex number has magnitude and phase angle. So you can represent this complex number by, for example, this vector. This vector represents this complex number. The length of this vector is equal to this magnitude, and this phase angle of this vector is equal to this phase angle. For different frequencies, you will have different magnitude and different phase angles, that is different length of this vector and different phase angle of this vector. So therefore, for different frequencies you will have a locus of this vector, and locus of this vector, that is when omega is varied from 0 to infinity, that locus is called polar plot. Is it clear? Here this frequency response is a complex number with magnitude and phase angle, and for different frequencies this magnitude and phase angle will be different. So you will have different vectors which will be representing this complex number, and locus of those vectors when omega is varied from 0 to infinity, that locus is called polar plot. So basically this polar plot conveys the same information as Bode diagram, however in slightly different way. Over there we had two different graphs, here the same information is depicted in a single graph, and these polar plots are relatively less detailed. This shape of the curve, that is not too much accurate in case of polar plots. So as just like our previous studies, we shall first learn how to sketch polar plots, and after that we shall learn how we can utilize these polar plots for the analysis and design of control system, that we shall learn later. So to learn the sketch of polar plots for different transfer functions, we start with very simple transfer function. G of s is equal to s, and the frequency response of this transfer function is obtained by substituting this s equal to j omega. So here is the frequency response of this transfer function, and this is a complex number. It can be written in the form of magnitude and phase angle. So magnitude of this complex number is equal to omega, and phase angle is equal to 90 degrees. So we shall plot these vectors for frequencies starting from 0 up to infinity. So here is the complex plane with real axis and imaginary axis. For omega is equal to 0, where is this point located? So this 0 angle 90 degree is a point over here. As you increase omega, magnitude of this complex number will increase. For example, for omega equal to 1, where is that point mapped? So for example, that will be this point is 1 angle 90 degrees. Similarly, 2 angle 90 degrees and 3 angle 90 degrees. So as you vary omega from 0 to infinity, you get this straight line. So for this transfer function, this is the polar plot. This arrow indicates the direction of increasing frequency. This point corresponds to frequency omega equal to 0, and the point at infinity, that corresponds to omega equal to infinity. And this arrow is in the direction of increasing frequency. Is it clear? So next comes this transfer function. Again, frequency response can be easily obtained, and this complex number can again be represented in polar form. That is, if we bring this j in the numerator, it becomes negative minus j, and that is the magnitude of this complex number is 1 over omega, and angle for all frequencies is equal to minus 90 degrees. So what will be the polar plot? Minus 90 degrees is, for example, this magnitude as omega, if omega is equal to 0, what is magnitude? Magnitude is infinity. Infinity angle minus 90 degrees is somewhere here. And then as you increase omega, this magnitude decreases. For example, for omega equal to 1, this is 1 angle minus 90 degrees. So where is that point? So 1 angle minus 90 degrees is over here, and further increase in omega will decrease the magnitude, but that will always lie on this this axis. Therefore, the polar plot will look like this one, and it is incorrectly written. This should be omega tends to infinity corresponds to this point, and omega equal to 0 corresponds to some point at infinity angle minus 90 degrees. Next we take this transfer function. Again, frequency response is easy. This is the frequency response. We can write the magnitude of this complex number and the phase angle. Magnitude of this complex number, you remember, is this one. The magnitude of the numerator is 1, magnitude of denominator is square of the real part plus square of the imaginary part whole square root, and angle of this complex number, when written in the numerator, it becomes minus tangent inverse of the imaginary part divided by real part, minus tangent inverse of omega t. So remember that for polar plots, we do not need very detailed information, only a very rough sketch is required. Therefore, if we have information about a few points, we can just draw some graph. For example, if we have omega equal to 0, which is the magnitude and phase angle of the frequency response. For omega equal to 0, if we simply substitute it over here, we get 1 over 1, which is 1, and written in the polar form, this is 1 angle 0 degrees. And for omega equal to infinity, what is situation? For omega equal to infinity, magnitude of complex number is 0, and what is phase angle of that complex number? Minus 90 degrees. So we have 0 angle minus 90 degrees. So in the complex plane, we have 2 points. One point corresponds to omega equal to 0, and the second point corresponds to omega equal to infinity. So how would you obtain the graph? Here detailed information in this graph is not required. Generally, we only need a rough sketch of this graph. So how should we sketch the graph? What we can see is that as omega increases, what will happen to the phase angle? Phase angle will become more and more negative. And what about the magnitude? Magnitude will decrease. So that is this point corresponds to omega equal to 0. For omega equal to for example slightly larger than 0, maybe we get this point. Phase angle has become negative, and it will become more and more negative, and magnitude of this magnitude of the vector will be decreasing finally to become 0. So if we use only information of these 2 points, then a rough sketch of the polar plot should look like this one. Can we also sketch it in this way? Is it also correct? No, because angle is for example corresponding to this point. What is the angle of vector from this origin to this point? That is positive. But what we can see is that angle is never becoming positive. So this graph denoted by dotted lines, this is incorrect. Also, what about this one? We had information about this point, and is it possible to have this graph to join these 2 points? Why? So angle, that maximum angle that we can have is minus 90 degrees. For example, corresponding to this point, what is angle of the vector from this point to this point? Greater than 90. But for this complex number, angle can never be greater than 90 in magnitude can never be greater than 90 degrees. So this graph is also incorrect. These 2 graphs are incorrect. And if you want to further refine this graph, you can determine a few more points. For example, the convenient point, which can be easily determined, will correspond to omega equal to 1 over t. If we substitute this point over here, so this 1 over t square is cancelled with this t square, so magnitude comes out to be 1 over square root of 2, and 1 plus j1, what is the angle of that complex number? Plus 45 degrees, and when brought in the numerator it becomes minus 45 degrees. So we have determined one more point which corresponds to frequency equal to 1 over t, where t is some constant, and then we can simply join these 3 points by a freehand sketch. So this is polar plot of this simple transfer function. Remember that in polar plots you do not need very accurate sketch, you only need a very rough sketch. However, one information that you will always require to determine accurately is the crossing of the graph on real axis. Why that is accurately required, we shall learn it later. However, this information will be required very accurately. So how we can determine the crossing of this graph on the real axis? So we can, for example, rationalize this transfer function, this frequency response, and determine the real axis crossover by substituting the imaginary part to be equal to 0. So if we rationalize it, we can multiply both the numerator and denominator by its complex conjugate. We have this expression. To determine the crossing of this graph on the real axis, we can substitute the imaginary part to be equal to 0. That is this minus omega t over this thing equal to 0. So what are frequencies for which this graph will cross the imaginary axis? Omega equal to 0 satisfies this equation, and omega equal to infinity also satisfies this equation. So these are the 2 frequencies for which this graph will cross the real axis. We have already determined the corresponding frequency response corresponding to these two frequencies. So we have already determined one point was over here and other point was over here. So this is the polar plot for this transfer function. Any question up to this point? So can you sketch the polar plot for this transfer function? Frequency response is easier to obtain, and we can also write it in the polar form, that is the magnitude of the complex number and the phase angle of this complex number. So please obtain a very rough sketch for this polar plot for this transfer function. Straight line with some slope. Up key observation, semicircle, but in the upper right half, upper plane, upper half plane. Any other observation? So we can determine a few points. For example, omega equal to 0. What is situation? If we substitute omega equal to 0, we have a real number which written in polar form, we have 1 angle 0 degrees. And corresponding to omega equal to infinity, what is magnitude? Of course, for this omega infinity, magnitude of this complex number is infinity, and the angle, what is angle? Angle is 90 degrees. We can determine a few more points. For example, this point is more convenient, and corresponding to this point, the magnitude is square root of 2 and angle 45 degrees. So here is the polar plot. This point corresponds to omega equal to 0, which is 1 and angle 0 degrees, and corresponding to this thing, 1 over t, we have square root of 2, maybe it is somewhere this point. The length of the vector from origin to this point, that is square root of 2, and the angle is 45 degrees. And corresponding to omega equal to infinity, you have a point somewhere at infinity. So this is the polar plot for this transfer function. One more thing which can be helpful in sketching this polar plot is over here. The real part is always equal to 1 and imaginary part is changing. So real part is always 1 and imaginary part is growing with frequency. We want to sketch the polar plot for this transfer function. Again, frequency response can be obtained by substituting s equal to j omega. This is frequency response, and we can also write it in this form. Divide both the numerator and denominator by omega n square. In the numerator you have 1. So this omega n square divided by omega n square is 1 written over here. This term is written over here, and this term is written over here. We have simply rearranged the terms. And for omega equal to 0, what is this complex number? This term is equal to 0. This term is equal to 0. 1 over 1 is 1 angle 0 degrees. Corresponding to omega equal to infinity, what is situation? So this term will be much larger than this term and this term. So as omega tends to infinity, we can just omit this term and this term. So g of j omega is over here. So what is magnitude and phase angle of this complex number? Phase angle, what is phase angle? Minus 180 degrees. So phase angle is minus 180 degrees and magnitude is 0 as omega tends to infinity. So again we have 2 points. One point corresponds to omega equal to 0, which is over here, and the second point corresponds to omega equal to infinity. Here this point is 1 angle 0 degrees, and this point is a vector. This point is 0 angle minus 180 degrees. So what do you think? What is the rough sketch of polar plot. Right. So it will cross the imaginary axis. Angle will become more and more negative. It will become more negative than minus 90 degrees, and the graph will be somehow somewhat like this one, starting from here, moving this one, and finally converging to this thing. So do you think that it will cross this real axis on this side? That is it possible for the graph to start from here, move like this one, and then reach over here? Is it possible? No, because angle is not becoming more negative than minus 180 degrees. So maximum angle that is possible is minus 180 degrees. Therefore, one more point which can be conveniently determined corresponds to omega equal to omega n, and if we substitute omega equal to omega n over here, so this j square becomes minus 1, which is written over here, and that is simply equal to this thing, 1 over 2 zeta angle minus 90 degrees. So where is that point? Somewhere over here. So joining the information of these 3 points, we have polar plot, uh, and that is depicted over here. That is a rough sketch of the polar plot, and you can also determine the crossing of this graph on the real axis, and for that purpose you will be required to rationalize this complex function, and then determine the crossing of this graph on the real axis and imaginary axis.